In this video, we're going to start to think about what is energy. How do we define energy? Where do we find energy? And what does it do within a system? And how does this start to relate to chemistry? So the first thing we want to think about is what is energy and why and how do we study it? So the study of energy in chemistry is called thermochemistry. You may also hear it called thermodynamics. And so thermochemistry studies the energy stored in the bond, so how two atoms are connected, and how this reaction or a reaction can either generate or absorb heat to provide energy to do work. So we're going to start to measure how easy it is to go from A to B or from B back to A. Is that energetically favorable or unfavorable? So the first thing we want to think about is what is energy? Energy is broadly the capacity to do work or transfer heat. And so we might be asking ourselves, what is heat? Heat is the energy used to cause a temperature change. And work is the energy to move an object against a force. And so in later videos in this series, we will look at heat and work specifically. But let's think about energy broadly first. So there are different types of energy, and these two up here at the top are related to each other, and these two down here at the bottom are also related to each other. So we often think about kinetic and potential energy. So kinetic energy is the energy associated with the motion of an object. So this is the energy when something is moving. How does it move? What does that do? In terms of chemistry, we tend to think about the kinetic energy actually as the thermal energy of motion. So in this case, the energy associated with the temperature. And so in chemistry, this can be defined as the motion or the thermal energy stored in bonds or other components. So potential energy is the energy associated with the position or composition of an object. So kinetic energy is the energy of motion. So if you have a biker rolling down a hill, so if this is a hill and we have someone riding a bike here, the kinetic energy is the movement of their motion, and the potential energy is the stored energy at the top. So chemical energy is the energy associated with the relative position of electrons. So how do these actually work in terms of energy? In later videos, we're going to start to think about what does it look like in a reaction? How does this work? So there are equations for kinetic energy and potential energy, but we're actually not going to look at those because we are mostly going to think about changing energy in a reaction or other systems. So energy transfer, we want the ability to think, how does this move from one place to another. So the law of the conservation of energy states, energy can be neither created nor destroyed. So energy can be transferred between objects with no energy loss between them. So we tend to say something like it goes from the system to the surroundings. So if we think of a box where in here is the system, that's the thing that we're studying, and the surroundings are out here. So we can see that in this case, the blue arrows are the energy leaving the system, and now they're going to the surroundings. But if we were to think about the energy going from the surroundings into the system, it would actually just be that they would move in the opposite direction. So now the energy is going to go back inside the system. So in this case, the system is the thing we are studying. And the surroundings is everything that exchanges energy. In this case, with the system. So we can think about this transfer between these two, and we're going to talk about how we measure this. But the energy moves from the system to the surroundings and back again. So in order to measure energy transfer, we need to start to think about the units. So there are two main units. We have calories and joules. So calories is the energy required to raise 1 gram of water by 1 degree Celsius. And so we tend to annotate that as 1 CAL or 1 small c. So then we have joules, which are the scientific unit, and this is 1 kilogram meter squared per second squared, and that just equals 1 joule. And so if you wanted to convert between these, 1 calorie is equal to 4.184 joules. So this is a standard conversion, and so the calories that we see here are broadly related to the calories that we see on packaging, saying how many calories are required for different food items that we might consume. So as we start to think about energy transfer, the first law of thermodynamics states all energy of the universe is constant. It's very similar to the previous law. The energy that is lost from the system is gained by the surroundings. So what we see is this direct transfer between them. If we were to have 2 buckets at the start, where inside bucket 1 there were 3 triangles and only 1 triangle in the other. If we were to see a transfer, what we would see is that there are now 2 triangles in both boxes because one triangle transferred from the top box to the bottom box. So this is what we see in terms of energy. So it's very difficult to measure the energy of a system at a specific point, i.e., what is the energy of the system right now? What about right now? However, we can measure the change in energy, or delta E, for a system, where delta E is equal to E final minus E initial. And so we are going to be able to think about that in all of these cases. So if we were to think about this in terms of a reaction, the delta E of a reaction is equal to the E products minus E reactants. So we could draw a little diagram where we have internal energy for the reactants and the products. And in this case, if we were to go in this direction, delta E is negative, or so this means energy is released. And so when we start to see these transfers, we can think about this. It's important to note that the E's here have been capitalized. This means that energy is a state function. State functions mean that they are path independent. Path independent means if we are measuring the change from this triangle to the circle, if we are measuring how far apart these are, the only measurement we're going to take is this measurement right here. If by chance we were to leave the triangle, go here, go all the way here, the distance between those points is actually still the same. It just feels like it took longer. So that would be a path-dependent measurement, where this is a path-independent measurement. So when energy is lost from the system, this is going to mean that delta E is negative. If energy is gained into the system, this means that delta E is positive, and we'll look at this more in a minute. In terms of a reaction, delta E is related to the products minus reactants. And we saw that on the previous slide where we looked at the change in internal energy between a reactant and a product, where delta E would be negative, and so energy will be released. If by chance you were to go in the opposite direction, energy, or delta E, in this case, is going to be a positive number, and that means energy is required in order to move from one to the other. So this energy transfer means that it's going to be gained from one and lost to the other. And in the next video, what we'll see is how can we calculate and really think about these energy transfers.